I'm Zach Waters.
And I'm Nicholas Cologne, and for our final lab project, we explored fizzo fringe patterns.
The phenomena of fizzo fringes was first described by Robert Hooke in his 1664 book Micrographia, where he talked about his observations of them in magnifying glasses. Newton further analyzed this principle in his book Optics, published in 1704. These so-called Newton fringes he used to analyze and gauge how closely his shape of his primary mirror for his reflector matched a known spherical convex lens. In the mid-1800s, Armand Fizeau experimented with an interferometer that resulted from light interacting in various mediums, and he even experimented with the interference formed when two surfaces touch each other. A simplified version with just a viewer viewing the fringes off-axis is used by opticians to qualitatively measure the difference in shape between optical flats. They express flatness error as a result of spacing of curved fringes formed between the test flat and the reference flat. Machining has also used Fizeau fringes to measure the accuracy of gauge blocks that they create to ensure their accuracy. Machining has also used Fizeau fringes to measure the accuracy of their gauge blocks that they create. This was quoted in Mituyo's factory results in 1966. This allowed for the quantification of ringing, a phenomenon where flat metal pieces stick together due to their flatness and the air pressure around them. Modern tests were proposed by James Burchett at the Optics College, where now spherical surfaces can be compared to a desired accuracy by using a computer graphic hologram to represent the desired shape.
As an example, we give the picture from one of our trials where we use two elements denoted test and flat. We measure the fringe radius y for fringe order m and make a plot of y squared versus m for each trial. Using our derivation from earlier, the slope of the trend line for this graph should be equal to lambda over r effective. The results for all 7 trials are shown below. We see that the value for r effective is lowest for trial 5, so those two surfaces are most closely matched in shape, and for trial 1, the r effective value was largest, meaning those two surfaces were farthest apart in shape. The different values for R effective for each of the trials lets us characterize the surfaces by which are more convex, flat, or concave than the other surfaces. Trial 7 was the only one where we observed straight Fizeau fringes, which means that these two surfaces were considerably flatter relative to each other than in the other trials.